Hi, and welcome to a very special Atlas tour. Special in two ways. It's a 360 degrees tour, so you can feel free to look around a little bit while I'll guide you through the cavern and to the Atlas experiment. And also because we're going to see some special places that you wouldn't even be able to see when taking one of the regular tours here coming to CERN. You can already see here in the background our beautiful mural painting of the Atlas detector. Just note that even it's big already, it's maybe only half the size of what the actual experiment will have to offer. But you'll see that later downstairs, so let's have a look. So here we are in the Atlas building, just in front of one of the elevators and the first layer of security check, which I'll go through and I'll meet you on the other side. So here we are just in front of the elevator that can take us down to the Atlas experiment. And you can already see here a schematic drawing of the detector and a few things that we are about to see underground. So just to give you a bit of an idea and a bit of a perspective, the whole thing, the experiment is about 45 meters long. It's about 25 meters high and 25 meters deep. It's more or less symmetric, forward and backward. The protons or particles in general, the hadrons from the Large Hadron Collider, they enter from the left and they enter from the right, and they collide in the very center of the detector. And then the detector is essentially some sort of camera, you could say, that tries to take a picture and tries to record and measure everything that leaves the interaction point. So particles that are produced, they will stream outside of the detector, and we try to measure everything that is produced in these collisions with our detector. By the different colors, you can also see that our detector, the Atlas experiment, is made of different layers, different types of detectors that all have their own purpose. They measure different quantities, they target different types or categories of particles. And we have at the very center, we have tracking detectors, so they are trying to reconstruct where the collision happens. They're trying to reconstruct where particles, at least charged particles, went. So they track the particle as it traverses through the detector. Then here in green and in orange we have so-called calorimeters, an electromagnetic and an hadronic calorimeter that measure the energy of particles by essentially stopping them. And one of them, the inner one, the electromagnetic, targets electrons and photons, whereas the other one targets hadrons, so particles like the proton or the neutron that you might know. Then further out in blue we have the Muon spectrometer, which is in principle another tracking detector that we use to measure the momentum of muons again. Muons being essentially the only standard model particle that is detectable in our detector that leaves the calorimeters, and we measure momentum of those again out here. To measure momentum in general, both inside and out here, you need magnetic fields. We have a so-called solenoid magnetic field in the center, and the very characteristic toroidal magnetic field in the Muon spectrometer. So what you see in gray here is superconducting magnets that provide a magnetic field to bend the charged muons so that we can measure their momentum and identify them in the Muon spectrometer. And then here you see beam pipe shielding, which is essentially just concrete that protects the detectors from radiation that happens close to the beam. And you'll see some of these components on our way down to the experiment. So we'll get the lift and go down about 92 meters underground to have a look at the experiment. So we'll take the lift down. Outside the actual cavern, there's an extra cavern that houses computing and cooling equipment. And then we'll take our way into the cavern, and we'll end up roughly around here. What is in this picture between the two big wheels that you see here, only that the left of the two big wheels will be moved towards the right one. This will be removed, and this part will be taken out so that scientists and engineers have a chance to get to the inside of the detector to do repairs and upgrades of the whole system. But let's take the elevator and have a look down. So let's take the lift down to about 92 meters underground. We're going to be roughly at the base level of the cavern. So as I said, the experiment is about 25 meters high. So the beam pipe is roughly in the middle, about 12 meters above us at so-called level 4, which we're going to pass by later on. The LHC in general is not horizontal, completely horizontal in Earth. It's slightly higher towards the Jura and slightly lower towards the Lake Geneva. And you can also see that in the experimental setup that there is this slight tilt in the LHC, the 27-kilometer ring that provides the protons for the collisions that we want to observe in Atlas, as I showed you on the schematic at the surface. So now we're at about minus 92 meters. Let's have a look. So here's another level of security, and I'm going to see you on the other side.
Thank you. You have been identified.
So now we are at the base of the experiment. If we look over here, we can already see sort of a glimpse of it. The orange structure you see here right next to me is in fact not part of the experiment. It's a support structure to hold one of the end caps of the toroid magnet that we'll see the better later on, that has been taken out of its design position and moved to the side so that access to the inside of the detector is possible. But you can already see here that building such an experiment at this complexity and size requires a lot of planning and thinking. There's hundreds of cables, of pipes, tubes, data going in, data going out. So many things you have to take into consideration when you design such an experiment, and we'll see a few of these things later while we explore the cavern together. So let's have a look. So now we're at the far end, towards the A side of the experiment, the anti-clockwise. So this way we're looking towards LHCb, and and towards Lake Geneva, whereas the other side is the clockwise side that points towards Alise and the Jura Mountains. You can here see already sort of one of these big wheels that I've shown you on the drawing at the beginning on the upper side of the lift that sits here, actually both of them put together, and then this big structure here is holding the end cap of the toroid magnet, as you can see already there. But let's go further up to have a bit of a better view. So this is level 4, and you can see the beam pipe there now, sort of roughly centered on this level, and then you can also see sort of the structure of these detectors that sit here at the very end, detecting muons that go towards the center. So it's a big wheel that is sort of symmetric. It has a symmetry in it, and points sort of towards the detector, trying to cover as much in terms of angle as possible and getting close as possible to the beam pipe. Alright, but let's go to level 6, which gives us the chance to actually go around the whole experiment together and get a view. And now we are at level 6, which gives us the chance to actually go around the whole experiment. But let's have a look here first. As I said, this is part of the Muon spectrometer at the very end of Atlas. Same way on the other side, as we're going to see later. And you can see very nicely this type of detector, which is a so-called monitor drift tube. It's essentially a tube with a wire inside and a gas mixture that charged particles, so muons that go through that gas, ionize, and then you get a readout signal at one of the wires. It's a fairly simple sort of setup, but there's another nice thing you can see here is that you have sort of different layers that always overlap each other a little bit, which is one of sort of the principles in designing such an experiment, that you don't want to give any particle that leaves the collision the chance to leave the detector unseen. So you build detectors that overlap slightly. There's other reasons to do that, to have these overlaps, but one of these is to sort of be as efficient as possible in reconstructing particles and not leave them any chance to leave the detector if it's particles that we can see. Obviously, there's particles like neutrinos that only interact through a weak interaction that we are not able to see at all in the detector. Only through indirect measurements we can get an idea of that. But then let's take a chance and to go around the experiment to give you an idea of the size of Atlas. So here we are at the A side of Atlas, and you can see, as I mentioned, with the schematic drawing, one of the big wheels that's usually sitting at the end of this structure here has been moved to the left. So you see two support structures here, which is the two big wheels. Then you see in the background the silver part is the end cap of the toroid magnet, which has been moved out and to the side so that we can get, for example, this piece, the big sort of reddish kind of element here with a lot of cables around, which is the end cap of the calorimeters. So the detectors that measure the energy of, for example, electrons and protons and so forth. And you can also see that these yellow bits, they're not part of the detector. It's platforms that have been moved in to allow people to work on the various components. and to get access to the inner parts of the detector, which you can not entirely see. Another thing that's very characteristic to see here and in general for Atlas is the toroid magnets that I mentioned before. It's this silvery structure with the red bands around it. There's 8 of these. This is the barrel toroids. The end cap also has an 8-fold symmetry. There's 1 at each side. But these barrel toroid magnets are essentially what gives Atlas this very characteristic shape and also this very characteristic toroidal magnetic field that bends the muons in the muon spectrometer to allow for this second step of momentum measurement. And you see also here these big sort of silver boxes with the black sort of layer in between. This is again parts of the muon spectrometer that do the actual measurement. As you can see on the left, if we go back to the wheel quickly, there's different types of detectors. So there's not just these tubes that I mentioned before, the monitor drift tubes. There's other types of detectors, both on the end cap and in the inner part, the barrel part. And that is because we have detectors for the muon spectrometer that can be very precise in the measurement, but are a little bit slower in giving sort of the feedback. And we have detectors that are really fast. And we need that for the so-called trigger system, which is a 2-level system that we have in Atlas. A first level is implemented in hardware on the detectors essentially. And the second level is on computers close to here, basically in a room next to the cavern. A system that has to decide whether a collision is of interest and whether we want to keep an event or whether we throw it away. And we actually throw away a lot because a lot of the collisions that happen at the LHC are not necessarily of interest, and we're not able to store all the collisions. So we have to do a sort of a very fast and a very hard decision on which events we want to save and keep for data analysis in the end. Right. And then another thing that I mentioned, the LHC is slightly tilted. If you look very closely down there on this orange support structure, sort of at the very top of it, you see sort of this pattern of orange feet and black holes. And if you look very closely, you see that the holes and the feet also, they increase in size from the left to the right. And this is essentially to correct for this slight tilt that we have to deal with. Right? And another thing you nicely see here, again, as I mentioned before, there's a lot of things you have to think about in designing such an experiment, like how do you get the voltage in? I mean, how do you get sort of, how are you able to steer your experiment, your detectors? So you have to send data and you have to get voltage and current in to have the detectors operate. You have to get data out, both physics data and just conditions data, so telling you what state the detector is in, what temperature it's at, and so forth. Talking about temperature, some of the detectors, certainly the magnets which are superconducting, they have to be cooled. The magnets essentially to minus 272 Kelvin about. Some of the detectors operate at room temperatures, others, like the tracking detectors at the very center, they operate at temperatures maybe around 10 degrees below zero in Celsius. So a lot of cooling liquid, for example, has to go in there. It's vacuum pipes. So all these things have to be taken into account, not just because you have to get the stuff in and out, but also because every piece of material that you put in the detector that is not the detecting element itself, essentially also those, have an influence on the measurements you take. Because the particles that are created in the collisions, they can interact with the material. They can lose energy by doing that, and then what you measure in the end might be sort of washed out due to that. So you have to take that into account. Also when you, for example, simulate events. An essential part of doing a physics analysis is also simulate events. So generate sort of non-real events, but as close as possible to real events in the computer, both for processes we know well and for processes we think nature might look like. We have to do that. And also for these simulations, you have to take into account this extra material, and you have to simulate the interaction or the possible interaction of particles with that material. Alright, but this is the first look at this side of the detector. So let's try and have a look at the other side of the detector. And also here in between, so now we're roughly at the middle of the detector in terms of length along the beam pipe of the LHC. You see there's a lot of infrastructure, lots tons, hundreds, thousands of cables that go in and out of the detector to be able to operate such a complex machine in the end. So now we're at the other side of the detector, clockwise in the LHC, and you can see it looks slightly different on this side. That is because here the end cap of the calorimeter is still sort of more or less in place. You can see sort of this silvery wheel in the end with the boxes at the side. That's the end cap that on the other side was moved out of the detector. Still you have these excess sort of platforms to be able to do maintenance and make it possible for the team to upgrade and repair the detector where needed. What you see here in the middle is the so-called small wheel, which is the first sort of layer, the first component, slightly smaller, yet still about 9 meters in diameter, of the Muon spectrometer. So it's to some extent similar to the big wheels, but it sits much closer. This is actually one of the components that within the next month or years we want to replace by so-called new small wheels that will allow us to do more precise measurement, to improve the quality of the trigger that I mentioned before, to do this fast selection of events, to basically select less wrong signals, so-called fake signals that in the end turn out to be not what we want. Yeah, and then you also see sort of this blue bit in the middle there, in the center of the big wheel, which is the beam pipe shielding. So in the center of that you have the beam pipe that at this stage is already just one pipe essentially, whereas sort of for most parts of the LHC you actually have two beam pipes where the two beams in opposite direction are separated. Here, close to the experiment, in general for the 4 experiments, the two beams are guided into one pipe and then brought into collision at the very center of the detector. If you look careful to the top, you also get an idea of one of the access shafts. This is actually the smaller of the two that we have. So essentially above each side of the experiment, there's one of these shafts to be able to lower things like the support structure in orange that you see down there, where again you also see sort of these pillars that change in height, and things like the nacelle to be able to work on these experiments and to perform repairs and upgrades. And we're going to see when we go to the other side, we're going to see the we're going to have a look at the shaft on the other side as well. Okay. Another thing that's very essential if you have lots of people working down here is ventilation. So you'll see that also in the other shaft that we're going to see in a moment. A lot of air has to be cycled through so that people can work here, and in cases of emergency that fresh air can be brought in and polluted air can be brought out. So now we're still on the clockwise side in terms of the LHC, but we are on the other side of the experiment where we came into the cabin. And also on this side you can see this end cap toroid that has been taken out of the central structure and moved to the side to make room to access the inner parts, to get things like the new small wheel or potentially also the end cap of the calorimeter out of the detector. And now we're going to go sort of down this hall a little bit to give you an idea. As I mentioned before, there's a lot of cooling infrastructure that also has to be in place to allow for the operation of the experiment. So here you get a good idea of, as I said, all the support structure and the ways you have to sort of take into account that some of the parts are movable. So you also have to adjust for that. So it's not just pipes, it's also sort of flexible elements in it. There is, as I said, you have to get a lot of cooling liquid in and out. You have to get electricity connected and all these things that you have to take into account when building an experiment like this. So let's have a look to the other side again to basically close our circle. So here we are again on the other side. You see the toroid end cap magnet on this side and the two small wheels. And now that we completed sort of our little tour around the experiment, you maybe also got an idea of the size. As I said, it's about 46 meters in length here, about 25 meters in diameter, so in that direction. And next we're going to see another special place you wouldn't be able to see on a regular tour that will give us a bit of an idea of the height. So we go up to almost the last floor. Here, if you look a bit in that direction, where I'm pointing here, you see sort of what I mentioned before, lots of ventilation. We'll see it better from the top again as well. That has to be brought into the cabin, and essentially also to climatize the cabin, that it's almost at a constant temperature all year long, so that some parts of the detector can operate at their sort of ideal operational temperature. Let's have a look. It's 3 more floors. So now we're almost at the top, level 11. I'm a little bit out of breath, but it gives you maybe a good idea of the size. If you look down there, this little platform, that's where we have been and looked at the A side of the detector. Then we took the tour to the other side of the cavern over there and back to here, and then came up to level 11. So it not just gives you a good idea of the size and a bit of time to look around, also gives me some time to also say a few other words. Obviously, such a big experiment also needs a lot of people to be able to run it, even to build it at the beginning. So Atlas is a collaboration with about 5,000 members all over the world, from many different countries and many different institutions that are a part of this collaboration, that together make it possible to build such a thing and to operate it. So when the LHC is running, which will hopefully happen again in 2021, we couldn't be here, that's one thing, and we would basically be trying to operate both the LHC and the Atlas experiment 24/7, because you essentially want to take any collision you can get your hands on, if it's good collisions. So the LHC is trying to run as much as possible, and we're trying to be as efficient as possible in recording the data, having the system up and ready at all times if possible. And in the recent past, we had more than 95% of the system up and running. For most of the component, it goes even closer to 100%, which is with about more than 100 million channels in the system. So 100 million independent readout elements that can give you data and that you have to put together to reconstruct the collisions that happen every 25 nanoseconds. So in principle, every second we have 40 million collisions that happen. And that is a rate that even particles leaving the collision point at the speed of light, which most standard model particles would do, you will have about three sort of collision events in the detector at the same time, because the particles created in one collision leaving sort of the detector towards the outer side, they won't reach the outside, the Muon spectrometer, for example, in case of a Muon. They won't reach it before the next collision or the second to next collision already happens. So it's also in terms of readout and understanding and disentangling sort of all the things that happen at the same time. It's quite a challenge, both on the hardware and on the software side, in the reconstruction algorithms that try to make sort of sense out of the individual measurements you have in the detectors. Another thing that makes this complicated is that with the bunches of photons, so it's not continuous beams in the LHC, it's bunches, roughly the size of a few centimeters, that with millions, thousands of millions of photons in each bunch that pass through each other. And typically there's maybe one interesting collision, so one that has, for example, a high momentum transfer, so that a new particle, that enough energy is in the collision that we can create a new particle. One might be interesting, but there's lots of others happening at the same time that are not necessarily interesting for the physics that we are interested in, because it's low momentum, low energy transfer, particles just barely hitting each other, not much happening, but nevertheless you see some sort of result of these collisions also in the detector. So typically in sort of the latest data taking run that we had about 34 on average collisions happening in one bunch crossing at the same time. So the detectors, especially the inner detectors, as I said at the very beginning, they are supposed to reconstruct the tracks of charged particles, and they're also supposed to reconstruct the vertex, so the point of origin where these tracks came from, where these particles were created. So they try to reconstruct those to disentangle sort of these individual, up to 60 or 70 we had at some time in the LHC, collisions that happen at the same time. Another very challenging thing, especially if you want to do sort of very, very precise measurements that in one or another way are influenced by these additional collisions happen at the same time. And since I talked about simulation earlier, also these kinds of events, which we call pile-up, so these multiple collisions happen at the same time, they have to be simulated as well to sort of get an idea, to get a better understanding, and maybe develop sort of methods to get more independent of these additional collisions. Because, for example, in the sort of next step of the LHC after the next run, so a few more years into the future, we have the high luminosity LHC in store, and there you'll have hundreds of collisions happening at the same time. So that's another reason why we have to do upgrades of the detector. This is one of the reasons why the new small wheel, the so-called new small wheel, comes in. One hopefully by the end of the year, and another one in the next shortest shutdown. Right, and then I said before, you can also have a look up. If you look up sort of the shaft here, this is the bigger of the two. It's about 18 meters in diameter. You see again lots of ventilation that has to happen to be able to work down here. You also see this red sort of installation going around. This is fire protection. This is sort of special devices that produce a special kind of foam that sort of suffocates fire, but you can still, so people can still breathe in it, so you can find your way out of the cavern without suffocation. But yeah, as I said, you can look up there, you see basically the underside of the roof of the building that is on top of the Atlas cavern, so almost where we've been at the start. And everything that you see in here essentially was lowered through one of the two shafts. Right? There's a few components like the end cap that in principle, I mean the calorimeter end cap, or the toroid magnet end cap that could be built on the surface and then lowered down in one piece, but most of these components were lowered down, and then down here with these cranes you see here, so the yellow is sort of a heavyweight lifting crane put into place. So it's a bit like building a ship in a bottle to build an experiment such as Atlas, because you don't have much space to move around. And as you see there's also not much space between the top of the experiment and the crane itself. So it's also, from that point of view, an interesting challenge to build such an experiment. All right. So I hope you now have a good impression of what Atlas looks like, and also maybe a little bit of what it takes to build an experiment such as Atlas. And we'll slowly make our way back down to the ground of the cavern, and then back up to the surface. So to go down, let's take the elevator. Alright, so on the way down we'll take the elevator, small little elevator. As I said, it's in total 12 levels. which make it quite an exercise if you have to walk it several times. But now we're going back to the ground level, the base of the experiment, and then make our way out of the experiment, out of the cavern, back to the surface again. Alright, so we're going back up. So we're still at about 92 meters underground. And we're going back up to the surface. And out of the experimental hall. If you have any questions, feel free to contact us on social media. Feel free to write us an email. You find all the details, all the social media channels on our webpage, atlas.cern. And we're looking forward to hearing from you. You can come to CERN and visit CERN all year long. It's free of charge. There's lots of interesting things to see. If we are still in the shutdown or again in the shutdown phase, you can also try to register for a visit to the underground, to not just have a virtual 360 tour, but an actual tour. But as I said, today we actually were able to visit a few places that you wouldn't be able to visit on a regular tour. So let me take you outside again. So here we are again at the surface in front of the Atlas building, in front of a beautiful mural. I hope you enjoyed the tour. I hope you learned something. I hope you got an impression of Atlas. I hope you had a look around, took advantage of the 360. You can just watch the video again, look where you want, stop where you want to have a look around. And as mentioned before, feel free to get in touch with us if you have any questions on social media. We're on Twitter, we're on Instagram, Facebook, or write an email if you have any questions on what we're doing and why we're doing it. And of course, have a look at the webpage before and follow us on all the channels. So, goodbye.